Thank you for all being here for the last tech talk of the day. We're going to be talking about a number of animation features we've added to Unreal Engine. These were developed over the past year for Fortnite. My name is Laurent Delayen. I'm lead animation programmer at Epic Games, and I've been working there for 16 years. We'll start by talking about Control Rig and how it was used in Fortnite for the Werewolf character. The Werewolf character was one of the big beats of Fortnite Season 6. It introduced for the first time in a game a character with dog legs. This presented a challenge for us because all of our animations are authored for human legs. We obviously don't want to reanimate the entire game for this new character. So how can we share these animations? But first, we need to understand how a Fortnite character is built. A Fortnite character is composed of multiple skeletal meshes. We have first a base skeleton, which is what you can see on the left in purple. We also call it the invisible skeleton, because it has no skin geometry. It's just a pure skeleton, just bones. On top of it, we overlay several character parts. We have at least two, a head and a body, but we also can have many accessories, such as hat, backpack, etc. We actually have many base skeletons in a game. We have a wide range of body types, such as small, medium, large, and extra large. And for most of these, we have a female and a male variant. All of these base skeletons share the same hierarchy. That means they have the same number of bones, and these bones have the same topology. But the skeleton can have different proportions. In Maya, we have constrained all the rotations to be identical to help with retargeting. However, bone translations can vary. On the screenshot on the right, you can see in green it's the medium male skeleton, and it's overlaid on top of the large male in pink. Look at the clavicles. You can see that they differ not only in length, but also in orientation. Character animation comes from a single animation blueprint asset that is shared across all these base skeletons. By main animation, I mean the locomotion, weapons, emotes, really what constitutes the animation of the character. So as I said, this runs on the base skeleton. And instead of these animation blueprints, most animations have been authored on the medium male skeleton. This was our reference skeleton, where most of the content was authored on. If this animation blueprint plays on a different base skeleton, then these animations get retargeted. Character parts that are overlaid on top of the base skeleton will share a subset of the base skeleton. But here, we're talking about identical bone transforms. So the animation can be transferred directly from the base skeleton to the character part with no retargeting. You can see an example on the right. In blue, we have the base skeleton, and in pink, this is a character part, the head. You can see that they share the neck, the clavicles, the spine, down to the root. Character parts can add leaf joints as needed. So in this example, the head adds face bones that do not exist in the base skeleton. Character parts can have their own animation blueprints and layer on procedural animation. At the bottom of the screen, you can see an animation graph. And this is actually the body part of the werewolf that we're about to look at. I have highlighted on the left. This is where we copy the pose from the base skeleton. So we copy transform from the base skeleton onto the character part. In the middle, we can overlay some procedural animation, for example, jiggle bones. And on the right, we have the final pose that we see in the game. So this is the body part for our werewolf. So you can see in yellow, we see the human legs. And in pink, we see the dog legs that we want. So we want to go for, all the base skeletons, all the animations were authored for human legs that have 2 bones. And now we want 3 bones. So can we just add a leaf bone at the bottom and go from 2 to 3? So we can't, because between the base skeleton and the character part, the transforms have to be identical. So if we just add a bone at the bottom, we don't get the shape that we want. So what we did here is we added another set of legs. So we have these new legs in pig, the dog legs, where the geometry is skinned to these legs. The human legs, we retain them, and that's how we get the animation transferred from the base skeleton onto this character part. So if we just take these character parts and put it in a game, this is what we would get. We see in green, this is the animation transferred from the base skeleton onto our body. They animate, but they're not skinned to anything. The actual skin legs have no animation because these joints don't exist in the base skeleton. So we tried IK first. Let's see what it looks like. And you can see it doesn't look great. IK, we're just spinning the feet from the dog legs onto the human legs. And if we try a more extreme animation, we see it's really a puppet pulling effect. We're just pulling these feet and pinning them, but we're not animating the other bones. So what we want to do is some custom retargeting. We want to find a way to transfer the animation between the human leg onto the dog leg. And we'll only use IK after that if we need to refine the pose. So we've created a custom retargeting solution using Control Rig. A little refresher on what Control Rig is. Control Rig is our in-engine rigging system that we have introduced at GDC a couple of years ago. A user can create a graph made of rig unit nodes, and the control rig will exist as a node inside of an animation blueprint. It will take as an input a full pose. The rig unit nodes will be able to modify transforms on that pose, and then as an output, we'll get a modified pose. So why use control rig here? So it's about using the best tool for the job. If you want to change animation playback, animation blending, then the animation graph is suitable for that. But if you want to manipulate bone transforms, then you can use control rig. So you could also write a C++ node. You can do that. But control rig allows you to do that in-engine visually without adding any C++ code. So you can do any kind of bone manipulation, procedural animation, retargeting, rigging. It's also high performance. Unlike the animation blueprint that has a VM that runs bytecode, when you compile your control rig graph, it's only native code running. So how do we transfer that pose from the human leg to the dog leg? So essentially, we're looking at the bind pose between the human leg and the dog leg. And we go through every bone of the human leg, and we find the transform that would take us from this bone to a corresponding bone on the dog leg. And we do this for every bone of the leg. So we can see the graph in control rig. This is for a single bone. And we repeat that for every bone plus the foot. So you'll notice there's one bone that we don't transfer any animation. It's the number 3 on the right. But that doesn't matter. Here's the result that we have. We can see now that our leg animates, and it's pretty close. If we look at the feet, they're not quite where they should be, where the animators intended the feet to be, but that's what we use IK for. So to finalize the pose, we put in IK, and now we pin the feet exactly to where they should be. So we go back to our animation graph for the body of the werewolf. I have highlighted first where control rig is, and then when we do the IK. So to recap, we get a pose from the base skeleton copied onto our body. We run control rig to transfer the animation from the human legs to the dog legs. We run animation dynamics if we need any kind of secondary physical animation. Then we run IK to adjust the position of the feet. And this is the pose that we get in the game. We showed a slightly more extreme pose. This is what it looks like, and it works. And on the right, this is the control rig graph that we use to do this entire retargeting. So this is a fairly simple example, but it really shows how it empowers artists. This was entirely done in editor by a technical animator with no programmer intervention. So as I was saying, control rig can do a lot more, including the biped rig that you see on this screenshot. If you want to learn more, Westbund will be presenting a talk at our learning theater called Enhancing Animation with Control Rig. It's on a rotation all week at our GDC booth. So stop by and take a look at the schedule to not miss it. Control rig will be coming as an early access feature in 4.22. So I mentioned that between base skeletons, we retarget animation. We've done some improvements to that as well. One of the drivers was to support squash and stretch in Fortnite. Animators really wanted to push the cartoony feel of the game. But in order to do that, you need to be able to animate bone translations. You need to be able to stretch the spine, for example. But that's not something that we're able to retarget before. So on the left, you see an example. This is the source animation on a medium male. As he jumps and lands, you really see the spine stretching. When we play this animation transferred onto the large body type, none of that carries over. So how do we retarget animation between base skeletons? We do that in 2 steps. The first step is the actual animation transfer. So in an animation graph, we have multiple animation nodes. These animations play clips of any kind. They define a retarget source. And a retarget source defines which skeleton was used when the animation was authored. So it tells us the proportions. When this animation blueprint plays on a different skeleton, if the source and the target skeleton are not the same, then we do some special remapping on the animation. The second point is we use space switching and IK to fix contact points. But that's something that we'll look at a little later. So how do we transfer this animation? I mentioned earlier that all the rotations are constrained together. They're all identical. So there's nothing to do there. We just read translation from the animation data and just apply it. Scale is relative, so same thing. We just read it. There's nothing to do. Bone translation, however, we saw it can be different between skeletons. So by default, we have 3 different modes. So let's take an example. Let's look at the clavicle on the screen left, and we want to stretch it. We want to take that bone and just pull it. The first mode is called skeleton. And what it means is we're basically ignoring the animation data. We just want to use the translation from the target skeleton. So we pull the bone in the animation, we ignore that data, so the result is we see nothing. It's just a bind pose. The second mode is animation. And here we're using the animation data, but we're not doing anything to it. So again, we have our 2 skeletons that we saw before. In green, it's the medium male, and in pink, it's the large body type. Because they use the same translation from the animation data, in the image in the middle, they overlap. They're identical. The third mode is animation scaled. We do the same thing, but this time we're going to scale the length of the bone based on a ratio between the target and the source skeleton. So now we get the correct bone length. It's retargeted, but we don't have the correct orientation. So in 4.20, we've added a new mode simply called Orient and Scale. We take the translation from the animation data, we scale it to have the correct bone length, but now we also reorient it, again, based on the difference between the target and the source skeleton. This is now the main mode that we use in Fortnite when we want to retarget translation. If we don't, we'll typically use animation and just use the animation data unmodified. So now we can see with the new Orient and Scale mode on the right, the animation is properly retargeted, and we see the spine stretch when he jumps and when he lands. So the second point is retargeting contact points. We can see on the left, this is our source animation. It's Jonesy playing the clapping emote. If we transfer this animation onto the large body type, and we do retarget the bone translations, because he has wider shoulders, this pulls the hands apart, and now they don't contact anymore. So if you're familiar with animation, you're very familiar with that. By the default, the hands are completely unrelated. They have no relationship with each other. So typically, a way that we address this is we create a new bone that's a child of the right hand, parented to the left hand, and now in the source animation, we have a bone that describes the relationship between these two bones. So if we play this animation onto the large body type, we can see it on the left. This new bone in orange shows us the difference. This is where the hand should be if it should contact, like in the original animation. So space switching is saying that. We're just going to make the hand, instead of being independent, is going to be relative to something else. And we use IK to move the hand to that position. So we control this using animation curves. In this clapping example, the curve would be just like that. At the bottom, it would say we want the left hand to be relative to the right hand. And at the top, it would say we want both hands to be independent. And these curves can drive animation nodes or rig unit nodes. So to recap the process, on the left, we have our source animation authored on a medium skeleton. If we just transfer it as it is on a large body type, we can see the shoulders are all scrunched up. If we enable bone translation retargeting, we have the correct shoulders, but now the hands don't connect anymore. So the last step is we enable space switching in IK, and we have both the correct shoulders and the hands contacting. So we use space switching and IK a lot on Fortnite for many different situations. Another very common one is the parent-child bone fighting. In this example, we're playing the guitar, and the guitar is a child of the right hand. We want the guitar to stay steady, but the right hand is doing these wild swinging motions, and so the guitar has to fight the position of the right hand. Now the animation is sampled at 30 Hertz typically, and we use linear interpolation in between keys. So due to subframe interpolation, the guitar is unable to compensate the motion of the hands, and we see this jittering. So because this is something that we use so much in Fortnite, we really wanted to make it a very easy process to set up. So we've added virtual bones in the engine. These create new relationships between existing bones. And you don't need to go in Maya anymore to add a new bone and re-export all over your animations into UE4. You can just instantly create a new bone and set up a new relationship between existing bones. So in the guitar example, we create a new bone between where the guitar sits and the chest, and now the guitar will be in chest space instead of being relative to the right hand. And we added 2 extra bones to put the hands relative to the guitar. And this is what it looks like. On the left, we have what we saw before, where the guitar is a child of the right hand and is fighting that motion and jittering. And on the right, we switch that over, and now the guitar is relative to the chest. There's no jittering motion anymore. So this is extremely easy to set up in blueprints and in control rig. In Fortnite, we have a setup. We can put the weapon in chest space, right hand space, left hand space, even floor space, and we can switch between FK and IK. So Blueprint is really powerful. The problem with Blueprint is its performance. And in Fortnite, performance is critical. We push upwards of 100 players. We're always adding new features, new vehicles. We're adding AI crowds. And at the same time, we're bringing Fortnite to more and more platforms, including platforms where we cannot run animation multi-threaded. So our typical approach is to let the creators run wild, and when it's time to ship a feature, we'll hand nativize it. We'll give it to an engineer, and typically he will take all the blueprint, turn it into C++, and make it fast. The problem is we've taken all that power away from the creators, and we've created a bottleneck around engineering. So we've added a few things to try to help that. We've removed the overhead from blueprint conversion. So you can drop a node, and you can choose which native type you can use to drive it. So NIK, for example, used to be only driven by a float. Now you can drive it by a bool or by a curve input type. This also reduces the graph clutter. There's a very simple example here. If you want to drive an IK node from a curve, you need to read the curve value, and maybe you want to process it. Maybe you need to negate that curve. Now you can do all of this natively, as you can see on the right. If you're familiar with the website Blueprint from Hell, you know that this can escalate very quickly. This is a very simple example here. But when you do it natively, notice the little thunder icon on the right. This means it's using fastpath. Fastpath means there's no blueprint execution. It's running at native speed. So we're trying to push that more and more and still give the power back to the creators. So we're doing more input processing into these nodes. We used to do bias, scale, and clamping, and now we've added range mapping and interpolation. For the Boolean input type, we've added blend in and out times, blend function, and a custom blend curve. The next topic we'll discuss is some improvements we've made to animation compression. Just like performance matters in Fortnite, memory matters a lot. As I said, Fortnite is an ever-growing game. We're always adding content, and we're always trying to bring the game to more and more devices, including many that have very limited memory. So what we do for animation is we run automatic compression. We have about 4,500 clips of animation in a shipping build. And automatic compression will run through every single one of these clips and try every single codec that we have with different settings in order to find the optimal compression for each one. This is paired with a strict error measurement so the quality can be trusted blindly. We don't want to break an animation that wasn't broken in the first place. And this works pretty well. We take an animation data size reduced by about 86%. But it takes 6.5 hours to compress everything. So it is too slow to enable by default. So what we do by default is we have a less efficient compression scheme, but it's really fast. And unfortunately, what happens is we ship animations that are not compressed optimally. So we've been working on the time that it takes for the automatic compression. The first thing we've done is an audit of the effectiveness of each codec, and we built a whitelisting process. So the number of codecs that we try went down from 35 to 11, and the time went down from 6.5 hours to just under 2 hours. The second thing that we've done is multi-threading it. So that took the time down to 40 minutes. And both of these are available in 421. But it's still not enough to enable it by default. When we have really long animations, compression is still a blocking operation in the editor, so you cannot do anything else. So what we're looking at next is asynchronous compression. We've also done some runtime memory improvements, and we've added per-platform animation downsampling coming in 422. This is one of these desperate times call for desperate measures type feature. We have some devices that are really tight on memory. And so what we do here is we just cut the sample rate in half. We throw half of the keys if the animation has more than 10 frames. This is a destructive operation, so clips can individually opt out. But this gives us an additional 30% reduction over automatic compression. We've also added float curve compression, also coming in 422. We have 2 compression modes. The first one, the default compression, retains the keys that you've authored in a curve, but just packs them more efficiently. The second one is a uniform curve compression. We sample the curve at a fixed interval based on the animation sequence sample rate, and then we compress it. And that not only gives us a better compression, but also a much better decompression time. It is 8 times faster reading this curve than a non-compressed curve. Animation compression is an area where we're planning to do a lot more work. I mentioned asynchronous compression. We're also working on plugin support. And we've been working with Nicolas Fréchette to bring ACL to UE4. That's his animation compression library. We've actually been working with Nicolas for quite a while now, including some of the things I just talked about. Nicolas is here with us. Let me invite him to the stage so he can tell us more about this collaboration. Thank you.
Hello, everyone. My name is Nicolas Fréchette, and my passion is animation compression. For the past 2 years, I've been implementing the animation compression library, which is an open source C++ library, It's super easy to integrate into any game engine, and it runs on all the major platforms. It also has some of the best performance in the industry today. You can check it out on GitHub and on my blog as well. And while the library is really cool, I needed a game engine to really see it in action and to be able to showcase it. And for that, I chose Unreal 4 for a number of reasons. First, it's a really mature and open source code base. Most game engines today don't expose publicly for plugins what I need for animation compression. But with Unreal, that was not a problem. I could easily find what I needed, go in, pull it out, and expose it to my makeshift plugin. And then I was able to publish all of that on GitHub for everybody to see, play with, and integrate back into their own game engine. Unreal, of course, has its own animation compression. It's been battle-tested for well over a decade in countless games. It's really solid, it works really well, and it serves as an important baseline for my research, against which I can compare against and track my progress. But equally important is also being able to publish these results. Many game engines and applications today explicitly prohibit benchmarking in the end-user license agreement, but that is not the case with Unreal 4. And of course, it's really easy to use. It gets out of my way and lets me focus on the fun bits. And overall, Unreal 4 is a great platform for research purposes. And working with Epic has also been a wonderful experience. Epic, of course, has a long history of supporting the community and working with them, from open sourcing their own game engine and as well the many Unreal dev grants. All the assets that they publish for free on the Unreal Marketplace, they were more than happy to work with me as well. Under NDA, they allowed me access to all the Paragon animations, as well as all the Fortnite animations. Well over 24 hours of total playback. And so all this amazing real-world animation data really allowed me to take my work to the next level. From implementing and testing out new features to trying out optimization ideas, or if I'm just closing down a new release, I can run extensive regression tests on thousands and thousands of animation clips. And I can make sure that the quality stays sharp everywhere and that everything else is rock solid. And all this amazing data is also perfect for performing extensive data analysis. I can look for patterns or trends in the data to look for opportunities for things that I can take advantage of or optimize for, which is most representative of the data we actually use in games. I don't have to make assumptions. If I have an idea or a question, I can just go and ask the data. And so Epic and I refactored the animation compression. We've taken the existing codecs and reworked them to be data-driven, removing a lot of rigidity from the old system. We have, of course, a brand new interface that exposes all of this to plugins for proper native plugin support. And we've, of course, kept the automatic compression that you know and love and that Laurent just talked about. All of this is scheduled for 4.23. And in the meantime, you can check out my own plugin on GitHub, of course. And you'll be able to find it very soon on the marketplace as well, entirely for free. And now, James Golding will finish up with even more cool features.
Thank you, everyone. And as Nicholas says, we're always interested in working with other people who want to use the engine as a basis for research. So if there's something interesting you want to do with us, do get in touch. OK, my name's James Golding. I've been at Epic 17 years, so I beat Laurent by 1 year. And I'm an engineering director working on the engine team. So the first thing I want to talk about today is something we call animation sharing. One of the things we wanted to add to our Fortnite game was a bunch of AI creatures. This was an idea that had been floating around for a little while, and we thought this would be a fun way to change up the game. But obviously, it comes with some challenges as well. We needed to find a way to minimize the CPU overhead of having to animate all of these creatures on top of the 100 players that we usually have in the game. And it was something we wanted to get up and running pretty quickly. So the basic idea we had was to share animation state between creatures, or pawns as we call them in the game. So the idea was, let's animate a small number of states, but then pass that animation on to a large number of creatures, and that way we can cut down the amount of work we have to do. So to get this going quickly, we used something called master pose component that Laurent actually mentioned a little bit earlier on. The idea here is you can already in the engine have one skeletal mesh component that does the animation work and then pipes that information onto a number of other skeletal mesh components. They're not actually doing the animation work. They're just showing the bones taken from somewhere else. So the first thing we needed to do was figure out what the key states we needed, which were going to be kind of looping states for our creatures. We wanted an idle state, we wanted a running state, and we needed a dancing state as well, because we're Fortnite, we have boogie bombs, and we wanted the creatures to dance as well as the players. So this is the first way we set things up. Normally on characters, we'd have an animation blueprint that runs the logic, looks at the character, and figures out what state it should be and what animation should play. But we wanted to centralize that system here. So we added a thing called an animation state processor. This takes each pawn, looks at various properties of it, and decides what state ID, what state it should be in. This can be implemented in C++ for speed or in blueprints if you're iterating on things, but it sort of centralizes the logic. In our game, we used the game playability system to set certain properties on these AI creatures, and that was what this system was looking at to determine which state it was in. So this is kind of where we started. We've got like one animation playing here and being shared onto all these creatures, so very low cost. But the problem is you can really see the repetition. They're all in time with each other. It looks pretty bad. So to fix that, we added some variations to each state. Depending on what state it was, we could add 2 or 4 or more different variations where we just offset in time the animation and then share it after that. So this isn't quite as efficient, but it does improve the quality. And this is kind of the result. You can see there's a bit more variation going on in the crowd. They look a bit more like individuals. So the next thing we needed was to add support for states that weren't just looping, but things that happened were triggered by gameplay. So that would be dying, for example, or attacking, or a full body hit. So I've done the dotted lines around these boxes to show these are on-demand states. They're created just when you need them, but they can still be shared. So if 3 creatures die at once, we only have to animate it once and then can share it between 3 of the creatures. The system automatically handles that. We can also put a clamp on the maximum number of these things we spin up. If you hit the maximum cap, we'll just use one of the ones, the closest we can find of the ones we've already created. So the next problem we hit was that when you jump between these different states, you really see a pop. So between the standing and the running and the hitting, there are these very obvious pops as you jump from state to state. You change where you're getting your information from. So to fix that, we use that idea of an on-demand state. But in this case, we create a blending state where we can take the existing idle and running states, blend them together, and then use that. Once again, this can be shared across multiple creatures if multiple of them change at the same time. We can also specify what the blend time between the different states is, and that can all be set up, and I'll show more about that in a minute. So this is what you get. It looks much better. And the final thing we added was additive states. Once again, these are on demand, but rather than replacing the state or blending between ones, they add on top of an existing one. But once again, they can be shared. So if you hit a bunch of creatures at the same time, we only have to create one of these additive states that adds on top of some existing state and then can be piped to creatures. So we made this all data-driven. We created a new kind of asset for setting this all up, and in there you can specify what the states you want are, what animations they should play, how many variations to have in each state, what the blend times are, and also some per-platform limits, which I'll talk about more in a minute. But this made it easy for the artists to go in and play around with different settings and make sure that things were looking good. So here's a bit of an example. I'll explain what's going on. On the bottom row are all of the different states that we're going to be in. And you'll see they sort of fire up when needed. And at the top are the on-demand blend states. So you'll see these only fire when you're changing between states. So you'll see our brave hero run past in a minute, pursued by a bunch of angry cube monsters. So at the moment, there's only the run state that's going on. But once they start attacking, you'll see there's some attacking animations at the bottom, and the blends are kicking off at the top. And then you can also see the dying state was coming in as we started bashing them with our pickaxe. So as we finish them off, the final death animation plays, and we're all done. So like I mentioned, we can do some interesting things with scalability with this system. So we can scale by platform. So when we're running on low-end mobile devices, for example, we can actually turn off the blending altogether. That was one of the things we did. We decided to sacrifice that and reduce the number of states we had. We can also reduce the number of variations on each state. So we might only have one on a low-end device, but a lot more variation to make things look better on a high-end device. We can also change this by distance. So again, that blending option of whether or not we should blend between states when transitioning, we don't do that on creatures that are a long way away, once again saving the amount of work we have to do. So this is a screenshot from this game mode running on Android, and it ran with a lot of creatures even on that platform. So here's the trailer we put out for the event. This happened in October. It ran for several days. We took over all the game modes in Fortnite, and people just showed up after the update, and suddenly there were creatures everywhere that they were battling. And so it really changed up the mode. People like me who are terrible at the game, it gave me something easy to shoot, which was pretty fun. And yeah, it ran on all the different platforms, and we really didn't have any performance problems. It went pretty well. So I'm going to talk briefly about some of the other parts of the crowd implementation. We did most of the work on the server rather than on the client. We wanted to really reduce the impact it was going to have on people's devices. So we need a fully dynamic navigation mesh because we're creating and building walls all the time. So that's constantly being rebuilt on the server. We sort of spread it out over time and limit how much work we do there. We use lots of the regular AI systems that are already in the engine, things like behavior trees, path-following components, AI controllers. But we did add some batching on top to try and optimize those systems. We use something called RVO, which is reciprocal velocity obstacles, to have the enemies avoid each other. It's quite a cheap way of doing that. We use navigation mesh movement, so the enemies just move around on the nav mesh rather than doing full character movement, which involves collision checks. We can avoid that work. So that all happens on the server. The replication graph is something we spoke about last year. That's the layer we have on the server which figures out what state to send to which clients. It's a big, important part of optimizing our server. We did some modifications to this to handle having all of these hundreds of AI running on the server. We sort them to figure out which ones are closest to the player. We cap the number that we send to each client, and we also send the ones that are near the player more data than the ones that are far away. And then on the client, we don't do too much work. We take these updates that are coming from the server, we simply interpolate between them, so they just smoothly move between where the server tells them they should be, and all the animation work that we've talked about, that only happens on the client. So the whole point of this talk, though, is talking about technology that's in the engine for everyone. So this is shipping in 4.22 as a plugin. It's very customizable. This is a simple test map of about 200 creatures here, and it takes about 1 millisecond on the game thread to animate them all. Because it is, really, it doesn't matter how many creatures you have as far as the animation work goes, because you're just doing the work and then sharing it between all the creatures in the crowd. But we're very interested in feedback. Hopefully, it'll be useful to people who want to do games with large crowds of things. It's a nice thing to have in the engine. We did have lots of discussions while we were working on it about where we could take this in future. Right now, each instance of the enemy still sends a copy of the bone transforms to the render thread. We could certainly change it to share that on the render thread. That would be one optimization. We did look into instance rendering for crowds rather than doing a draw call for each crowd member, but we found that game thread performance was really the main bottleneck here rather than draw calls, so we didn't need to do that in the end, although it's certainly something you could do. And you could go even further, and rather than drawing separate skeletal meshes, you could use quads, imposters like we do with trees. OK, the next feature I'm going to talk about is something we call animation budgeting. Last year on this stage, we talked about some of the other things we've been doing to improve and try and manage animation performance in a very dynamic and game that's always changing in lots of different situations. So we added something called the Significance Manager last year. The idea here is that you look at all the players that you can see, and you figure out which ones are the most important, and you put them into buckets. And so this prevents you from having too many players that are being run at high quality, even if they're close to you. And the main thing we used to control quality was something called URO, update rate optimization. And the idea here, oh wow, it plays GIFs really badly. But the idea here is that rather than running the animation logic every frame, you can run it every 2 frames, every 4 frames, and interpolate between the results, or even snap between the results. So this does work, and it does definitely help a lot. But the problem is, there is, even when there's a lot of players near you, and you add more and more players, there is still some incremental cost to every player that gets near you. So you get something like this. You can see the sort of inflection points as we're hitting the bucket size limits. But even at the end, as more and more players come near you, then you start to go over budget. And we've been doing some various events in the game where we get a lot of people together to do something interesting. We really wanted to handle those kinds of situations much more elegantly and stay within a fixed budget. So the way that animation budgeting works is it's similar to dynamic resolution for rendering. We work within a fixed budget, and we will adjust quality to hit that budget. So it's great. The more and more players you have, you're still going to hit some fixed budget, and we're going to scale down quality. So now when we're optimizing for quality and not for performance. Another nice benefit of this is on the low end, when there's just a few players around, we can actually lavish more CPU time on them and improve the quality because we know what the overall amount of work we're going to do is. As we implemented this, we wanted to make sure it had minimal cost as well. So we needed a system that was not going to add a whole bunch of overhead that made it pointless. So the first thing we need to do to implement this is estimate how much work we're actually going to spend on animation. So we can do this by taking the total amount of time we spent doing animation work, dividing that by the number of meshes we're animating, and then smoothing that over time to give us kind of a rolling average of the work unit, as we call it, the amount of time it's going to take to animate one skeletal mesh. So if we're in budget, we end up with something like this. The way this diagram works is each box is one mesh that we're animating, and at full height, it's running every frame. It's at 100% rate. And so in this case, we've got a bunch of meshes, we're running them all at 100%, and we fit within our budget, so that's fine. But if we just add one more mesh, now we're over budget. We're not going to be able to get all that work done in time, so we have to do something about it. If we run the animation at half rate on 2 of the meshes, it effectively makes the boxes half as big, and now we fit into budget. So this is kind of the general approach. This is a bit more what you'd get in a real game. There are some meshes where we say we definitely want to run these always at 100%, things like the player themselves. And then we'll have other meshes that are running at maybe quarter rate, third rate, half rate. And we just change all these knobs until we can make sure that we are fitting all the work we need to do inside the budget that we've set. So this is how it works in practice. It works really well. The dark blue line is before, where you suddenly turned around and you saw a bunch of people, or people just arrived, and suddenly we're way over budget. And this is not great. We're going to start dropping frames. We're trying to hit 60 hertz after all. But with the budgeter on, we're now going to crank down those knobs. We're going to lower the quality to make sure that we hit the budget we're looking for. So once we had this up and working, as always, you find some things out, and we had to fix some issues. So the first problem we had was not dabbing bananas. Dabbing bananas are amazing. But what the problem was when you crank those knobs down too far, you start to get unacceptable quality. So at full rate, it looks great. At 25%, so you're running it at sort of quarter rate, it's still OK for someone that's far away or in situations where there's a lot going on. But at 10% rate, only 1 in 10 frames, it really isn't something we want to ship. So we have to put a lower quality on that. And this is similar to the way that dynamic resolution works for rendering. There's usually a lower limit you're willing to go to in terms of rendering resolution. Another thing we did was to cap the total amount of meshes that we use interpolation for. So we can run animation maybe at half rate and interpolate between the results, but that does have some overhead over simply skipping the work. So we limit the number of meshes that we do interpolation for. We also added another option in terms of controlling cost. As we mentioned at the beginning, we have this master pose option where it simply copies transforms from one mesh to another. Normally in Fortnite, all of the different cosmetics you have, backpacks and hats and things like that, run their own animation blueprints with extra logic. So doing a character is actually doing 4, 5, 6 different animation blueprints. But we instead can just copy the bones from the base mesh and use the reference pose for bones that we're missing. And so it gives you another level of quality and reduces the cost to give us more options. Another change we made in the last year was that rather than ticking all the players that were near you, we used to do this for things like footsteps. We found that when you have a lot of players densely around you, you really don't need footsteps from all of them. So we just take the nearest n and tick those and stop ticking the other ones. So a problem we did hit as we were adjusting all of these different controls to adjust quality was doing things like turning that master pose on and off really does change the look of a character. So you get some nasty sort of flickering artifacts like this where you're turning the features on and off even when they're close. So we throttle state changes to avoid this. We say you can't change some of these parameters too quickly. Having said that, one of the problems we have when we start limiting the speed at which we're allowed to change these things is that when there are very quick changes in load, when, for example, you turn around and see a huge pitched battle going on, we fly way over budget and it takes us too long to recover. So this top line, the blue line, is where we suddenly see a big load and we compensate, we turn things down, but it takes us too long to respond and we've overshot. So what we did to cover that was in cases where we're very over budget, we'll allow things to change more quickly so we can recover more rapidly from those sorts of problems. So here's a kind of example of lots of things going on, and we're able to handle this much better now. We can look at the overall amount of work, we can scale things back, and it really is not too noticeable. And like I said, we've done some events where we've had very large crowds in a very small space, and it does handle those situations as well. So once again, this is a feature we're making available in the engine so that anyone can use it. It's in 4.22, which is coming out in the next week or so. There are lots of options, like I mentioned, for per-platform scalability. You can choose what the budget is on different platforms and how aggressively you want to control some of these different things. We've also tried to make this really efficient. It's a data-oriented implementation. tries to be really cache-friendly and keeping all of the state together so we can really work very quickly to determine what work needs to be done by which components. It's implemented as a new Skeletal Mesh component class, so you can opt in just for some of the meshes in your game. It's not an all-or-nothing solution. As well as doing this system to try and budget, we also made a lot of optimizations to the animation system. And of course, these just come as part of upgrading to 422. I'm not going to go through all these now, but for those that are interested, you can scroll back and pause the video later. But like I said, there's a lot of optimizations that we made that really helped. OK, the final thing I'm going to talk about today is, very briefly, is the new Skeletal Mesh Simplifier. For a little while now, we've had static mesh simplification right in the engine, so you can take a static mesh and reduce the quality, reduce the number of triangles. But now we've added in 422 skeletal mesh reduction. So like Nick Penwarden mentioned in the keynote, you now have all the tools you need to try and scale the quality of your assets. We're really happy with the results of this. It's about 6 times faster than the solution we were using before. It uses the same edge collapse approach, using a quadric error-based decimation. And per LOD, you can choose whether it's a triangle or a vertex budget, and you can also choose to reduce the number of bone influences in each LOD as well. But there were some problems with skeletal meshes that were kind of unique to that, different from static meshes. As Laurent mentioned at the beginning, we actually author our characters as a separate head and body mesh. But when we reduce those separately, it often reduces the vertices around that seam in different ways, and so you get these nasty cracks. So we needed to find some way to solve that. So we added an option called lock free edges, which essentially tells the simplifier not to touch the vertices that are on a free edge of that mesh. And so that way, we can guarantee that the two meshes will fit together again perfectly after simplification. Another problem we ran into is that some parts of the mesh would get oversimplified. So for example, on this creature here, when we simplify it, the eyes turn into sort of weird cubist shapes rather than nice round holes like they're supposed to be. It's not really something that we would like to ship. So we added an option to specify certain important bones, and then vertices which are weighted to those bones will be left alone. You can kind of choose how much less to simplify those things. But remember, it's still hitting the same vertex or triangle target, so if it's not taking the vertices away from the face, it's taking them away from somewhere else. So it'll be more aggressive to other parts of the mesh. Here's kind of an extreme case where we've told it not to touch the face at all, but to take all the vertices from somewhere else. But you can see it still handles it pretty well. And remember, this tool is not just for weapons. We use this for not just for players and characters, but we use it for all of our weapons as well. And it's been doing a pretty good job. Right, that's the end of the presentation. I'm going to invite Laurent and Nicholas back to the stage. Right, well, thank you very much for coming, and enjoy the rest of your GDC.
Thank you.
Thank you.